Hi, everyone. My name is Shaariq. I am a software engineer here in Johannesburg, and I am currently working with AI and large language models. But today I thought maybe we could speak about video games because I would imagine it's a pretty popular hobby amongst everyone here at BBD, at least most of us. And also because I think in recent times, over the last couple of years, there's been this trend where video games come out and they feel unpolished and unfinished, right? It feels like you're getting an unfinished product. The game performs very poorly, and also it's uh, it's just not fun to play anymore, right? So I wanted to look at why optimization is important. Um, so the biggest thing is it impacts your experience when playing a game, right? If the performance is not good, you're going to be somewhat frustrated and you're not going to enjoy playing the game. You're not going to want to play it. You're just going to probably uninstall it and move on to the next one. Um, but when you optimize a game, it allows software developers to ensure that the graphics are good, that you get high FPS, um, and that your controls are very responsive, right? And if you do all of this, it creates an immersive experience regardless of the hardware that you're on, because not everyone is playing on a high-end system, right? And these games, they need to be able to perform everything. It needs to be scalable. However, this is a very difficult task. It's quite challenging for a number of different reasons, right? I think the biggest and main one is the deadlines from publishers and studios, right? And if you follow a lot of news surrounding video games, you'll see this, where where publishers will place really tight deadlines on games. They'll announce like the release window like a year from now, and like we're gonna have this game out, and then the developers are under a huge crunch to try and get the game out to consumers. Um, and because of this, writing clean code and optimizing the game properly is not a priority. So oftentimes this will be left for post-release patches. So the game comes out, it's in a horrible state. I'm sure we all remember Cyberpunk when that came out. It was really bad. Um, and yeah, we had to wait like for patches every month or months from now, and then it takes like a year or two until the game finally feels finished and polished. Another thing is video games are getting a lot more complex, right? There are these larger open worlds, there are high quality graphics and stuff like that. So ensuring that the code and stuff is clean and optimized is quite challenging. And then also there's the iterative nature that needs to be taken into consideration, because games are constantly evolving. It doesn't just come out and then it's finished, right? There's constantly new patches, new features, new updates, all of that. And when you add this, um, what happens is inadvertently performance may take a hit. So developers need to be aware of this and constantly be vigilant and ensure that they always maintain optimal performance. Right, so let's look at some of the considerations software developers have to take a look at. One of the biggest ones are the hardware considerations. There are multiple different platforms that they need to develop for, the main ones being consoles, PCs, and mobile devices. Um, so for consoles, I would say it's a little bit easier because the hardware is like almost standardized and it's the same. There's like a few consoles you're developing for. There's not a wide range of different hardware. So it's you have tighter control. It's easier to optimize. Whereas there's a bigger challenge when you come into PCs, right? Because it needs to be scalable. Because not everyone, like I said earlier, has a high-end PC. It needs to be able to run budget systems. And then there's also a wide variety of different components. There's like dozens of GPUs on the market, dozens of different CPUs on the market, and you need to make sure that your game can run all of these different systems. So when you optimize for PCs, a little bit more difficult. And then there's also mobile devices. I'm not personally a big fan of mobile games, but from what I know, there's also a wide range of devices, so many different phones, and they're not as powerful as a gaming PC. So the big challenge there is um, there's a focus on efficient resource usage. You need to make the most of the little you have so that that game still gives the users a smooth and enjoyable experience. Um, Fortunately, game developers have a lot of tools to help them um, when developing for all of these different platforms. So let's take a look at some of them. We have graphics APIs. The two most popular are DirectX and Vulkan. They have a few differences. So DirectX is a collection of APIs that happens to include a graphics API as well, whereas Vulkan has a dedicated, it's a dedicated graphics API, so that's its sole purpose. Uh, DirectX is better suited for CPU and GPU intensive games. And when you compare the two, it would, in most benchmarks, it looks like Vulkan has higher FPS, maybe by about 5%, whereas DirectX is a bit more stable, so it doesn't have as much drops in your FPS. And Vulkan also has lower overhead. It uses fewer system resources such as CPU computation as well as memory. So that is also something to take into consideration. I think the biggest thing is DirectX is for Windows only. I'm on a Windows system, so I don't mind that. And if when I have the option, I prefer to use DirectX over Vulkan anyways, because visuals, especially things like weather effects, seem to be just a little bit better, and I don't mind losing out on the higher FPS over a more stable experience. Whereas Vulkan, it's cross-platform. So it works on Windows, it works on Linux, it works on macOS, Android, I think console too, pretty much everything. So it's a little quicker to use Vulkan if you want to release a game on multiple platforms. Right, and then we also have the game engine, and I'm sure you've all heard of these, Unreal Engine and Unity. They're quite popular. So developers will either use one of these two, or they may use their own custom engine if they want full freedom and control. There are also quite a few differences. Unity is a bit easier to use, a bit more user-friendly, and it's better for low-end systems. So you'll see a lot of mobile games will be made using Unity, whereas Unreal Engine focuses on fast rendering, raw graphical power, the real next-gen games. And they also come with built-in features to help optimize games for you. So Unreal Engine has what is known as the Unreal Profiler and Sequencer. So this allows you to look at things like CPU, GPU, and memory performances. So you can easily identify your bottlenecks and know where to go in the code and uh, tweak it to get better performance. There's also instancing, which will render multiple of the same objects. So if you have a scene and it has like a bunch of trees in it, the instancing will render it all at once with one single draw call. So that frees up some GPU computation. There's also built-in level of distancing tools, which I'll touch on a bit later, and virtual texturizing, which will stream textures only as you need them, rather than loading it all at once into the GPU. And then Unity also has a burst compiler, which will translate the C# code directly to the targeted system. So it's a bit more efficient. It also has the entity component system, which promotes data-oriented design, which helps with multi-threading. So if you have a large number of entities, it helps you better efficiently handle those. It also has batching, which is similar to the instancing, where if multiple objects use the same materials, it will load them all at once rather than having to do it individually. And it also comes with an asset store. So it has built-in assets and plugins which are pre-optimized for Unity. So they're a little bit more efficient. Right. So now we can look at some of the more finer things you can do to optimize your code. The first one, very common in video games, is level of detail. You'll see this a lot in massive open worlds. So this will adjust the complexity of an object based on the distance from the player or camera, right? So the closer an object is, the finer the detail, the textures, it looks higher is. But the further it is, it will use less expensive resources with a lower polygon count or lower resolution textures or both, which will help free up a lot of valuable processing power. I do have some pseudocode here to show how it works. So normally an artist will create multiple versions of the same object. So if you have like a skyscraper, for example, in a city, they will create different versions of that, right? There'll be one that's really high res when you're there with like really good reflections, really good textures, really good windows, for example, and it looks really good. And then they'll like scale it down and make like pretty simplified versions of it. And then what they'll do is they will calculate the distance of the object, of the player, sorry, or the camera to that object. And then if it's within like a certain range, they will render the most appropriate object for that, right? And then we also have another very common thing known as culling. You may have seen this if you like to abuse glitches in games where you go under the map. I have this picture of Starfield where you can actually like jump under the map and you can go and find this hidden chest and get unlimited money. And you'll see when you're there, there's a lot of objects that don't render, such as like the floor over there and like a bunch of different buildings, right? So this is in part due to culling, which removes the need to render objects that are out of sight. So there are three main types of cullings. The first one is frustum culling, which uses the concept of a frustum, which is like a cone-shaped object that will represent the player's field of view, and only objects within the player's field of view are rendered. So if the player doesn't see something, there's no need to load it into the GPU and waste that resources. It's only when they like turn around and look at it, then you can bring it in. Occlusion culling, this is when if an object is hidden by another object, there's no need to render it. So like again, if you have a skyscraper and you have like a park behind it or like roads behind it, because the player can't see it because it's hidden by that skyscraper, you don't need to render it until the player is close enough or it's in view. And then another one is backface culling. This one's also very common. So common, in fact, modern GPUs have dedicated hardware for backface culling, making it very efficient. So this takes advantage of the fact that objects have both a front and a back, and you don't need to render the back because the player can't see it. So you'll only render the polygons that represent the front of the object that's in view for the user. And then we can also look at texture filtering. So there are two main types. The one is MIP mapping. So this is when you pre-generate lower resolution versions of textures. So you'll have an original high resolution texture, but it's not always necessary to render this, right? Because if you are far from an object in a video game, what it looks like doesn't matter too much. So what you want to do is based on the distance to that object, you want to render the appropriate MIP map. And this is done by continually halving the resolution of the original MIP map, as well as applying filtering algorithms to keep it smooth, keep it looking what the original one looked like. However, you bring down the detail, so you make it lower res. And this is good for memory use as well as GPU processing power. And then we have a really fun one, anisotropic filtering. You'll see a setting for anisotropic filtering in almost every video game where it's like 2x, 4x, 8x, and 16x. And I think this one is less about performance and more about user experience. So I'll give an example that better explains this. If you have like a ground and that ground is made of cobblestones, right? If you don't have an isotropic filtering, it's going to look good around the player, but then as you look further into the distance, it starts to look flat and it like starts to smoothen out and lose a lot of that grainy detail. So, and that's what happens when in video games when you look at something at an obscure angle or an obtuse angle rather. So anisotropic filtering does some really smart calculations to sort of keep it looking realistic as far as possible without using too many resources. But compared to MIP mapping, it does come at a slight cost, right? And then we get to the most obvious way to optimize code, and this extends beyond video games, and that's writing clean code. One of the main things you can look at is your algorithms. So algorithms they play a big role in physics engines as well as the game logic. So because it's a pivotal part of the game, you don't want to use algorithms with high space and time complexities. You want to use something that's a bit more efficient. Also, you want to avoid recursion. If you've built some simple games before, you'll notice running in a loop. You really don't want to do recursion because it uses a lot of resources and it's quite inefficient. You can also use more efficient data structures such as quadtrees and octrees. Um, these are good for physics engines, especially regarding collision detection. And then we also have memory management. Memory leaks are never good. Fragmentation is never good. So you want to use best practices, use things like property allocation and smart pointers, which will automatically deallocate things as soon as you no longer need them. And then also multi-threading. Every single console, every single gaming PC has a CPU with multiple cores. So it's good to make use of all of them. You can have multiple threads, and a video game is like super complex and there's so much going on. So you want to separate things. You can have your physics engine running on one thread, your audio running on one thread. If you have to load more levels, you can do that on another thread, and that can all free up the main thread for only like rendering and the game logic. And yeah, that's it. Thank you for listening.